gives me immense pleasure to have Professor Mahadevan from Harvard today. Maha did his BTech from IIT Madras, and then he moved to Stanford to do his master's and PhD. After brief stints at Urbana-Champaign and Chicago, he took a position at MIT in around 2003 or something. And then he also subsequently held positions in the University of Cambridge. And since 2003, he's at Harvard. And now he's a full professor there in the Department of Physics, Mathematics, and Evolutionary Biology. So there are many accolades to his name. So Mahadevan he's a Guggenheim Fellow, a Simons Investigator, a Fellow of the Royal Society, and a member of the American Academy of Arts and Sciences. His pursuits have earned him an Ig Nobel Prize in Physics in 2007, and he has received the prestigious MacArthur Fellowship in 2009. So I quote the citation. He got it for applying complex mathematical and mathematical analysis to a variety of seemingly simple but vexing questions across the physical and biological scene. So for Mahadevan, everyday worlds holds great fascination, be a crumpled paper or breakfast cereals, cracking of mud, or shape of a leaf, or similar things, shape of an apple. So he uses basically mathematics and physics to explore these commonplaces phenomena and tries to unravel some fascinating things. So without further ado, so let us welcome Professor Mahadevan today here, and he will tell us about Kirigami, a story of papers, cuts, folds, and geometries. Welcome.
Thank you. Can people hear me?
Yeah.
Everywhere? Okay, great. Thanks. It's a small enough audience, so please ask questions when you feel the wish to do so. I hope there can be a conversation rather than me talking to you. I also don't like to talk from above, but I think I may have to because I have to use the clicker. So forgive me if I'm going to go up and down. And if you're willing to come closer, you can. I don't bark, I don't bite. Okay, so as Arnab said, I want to tell you a little bit about Kirigami, which is actually depicted here. So you take a sheet of paper, and if you make cuts in it, you can essentially create the I, the R, the K, and so on and so forth. And when you essentially fold it, things are popping out. So it's an old art form, but not nearly as old as origami. And maybe I should tell you a little bit about the history of origami and kirigami. Origami is not Japanese. Origami is actually a Chinese art form, but was really beautifully expanded, amplified in Japan. Origami, perhaps some of you know, comes from the Japanese words for paper fold. So ori is fold and gami is paper. Kirigami comes from the Japanese for cutting and paper. Kiri is to cut, and gami or kami is fold. Paper, excuse me. All right, so this is a topic which artists know very well, and it's over the last few years that colleagues of mine, myself, some of the students that we work with have started getting interested in trying to ask a very simple question, but the answer to the question is not at all simple. The question is, how do artists essentially recognize what to do when they essentially take a piece of paper and fold it to make complex objects like a dragon or a crane or a face, and similarly with a piece of paper, how do you essentially cut it rather than fold it in order to be able to do that? So artists, of course, use experience in experiments. Can we, as scientists, mathematicians, physicists, engineers, I'm not going to differentiate between any of these, can we essentially understand what they do? So that was somehow the motivation, certainly for me, with the end goal of trying to ask, can you essentially construct algorithms which allow you to essentially solve the inverse problem. So solve what artists do intuitively, what scientists may be able to essentially try and construct algorithms for. So these are simple examples of origami. So if I take a flat sheet of paper, you know paper cannot stretch very easily but can bend relatively easily. But it can only bend in one direction relatively easy. If I try to bend a piece of paper in two directions, it's impossible, almost impossible, and this is a consequence, it's a physical consequence of a very beautiful idea that goes back to Gauss. It's Theorema egregia, which says that if I essentially take two surfaces, then they are map one, I can smoothly essentially deform one onto the other if their Gauss curvatures are the same. So if the Gauss curvature, for example, of my head, which is non-zero, it's positive, I cannot essentially flatten it out unless I stretch it. So that's why you can't flatten the Earth. That's why essentially, in fact, that's why Gauss invented the subject of differential geometry, which of course has ramification and implications everywhere in science. What can you do otherwise? So if you can't do that by basically stretching, what can you do by folding? And so artists recognized a long time ago that by essentially introducing creases, you can, for example, approximately tile a hyperbolic plane. A plane which has a negative Gauss curvature. Of course, you can't again do that with a piece of paper smoothly, but if I introduce these creases, you can essentially do exactly that. So you can construct an approximation to a hyperbolic plane, and the approximation becomes better and better if I make the folds smaller and smaller, and therefore I am able to approximate this plane better and better. This is another example. This is an example where you've taken a piece of paper and folded it into the form associated with the helicoid, if you want, and a helicoid and catenoid, in fact, can be mapped onto each other very beautifully. This is a very, very nice problem in differential geometry for smooth objects. Here, you can do this with non-smooth objects, where you've essentially given up smoothness, but the consequence of giving up smoothness is that you have the ability to now get approximate shapes. And a theme right through this talk, to paraphrase, I think, Mark Katz, is to say, be wise, discretize. Forget about the smoothness condition. Can we essentially now do many interesting things as soon as I forget the smoothness condition? And how much smoothness do I forget? In this case, I will have C0 surfaces, or even what I'm going to call C-1, so surfaces which have cuts. They're not even continuous. They're not even functions. So that's origami, but I'm not going to talk about origami today. I'm going to talk about kirigami. Kirigami is its unheralded cousin, not so well known, but should be well known, where instead of playing with the configurational geometric degrees of freedom, where I take a sheet of paper and I essentially introduce creases, now I take a sheet of paper and I make cuts. Okay, so I violate the ability to even create or define something like a function, because as soon as I've essentially introduced cuts, I'm doing a lot of damage. Topological degrees of freedom are what I want to control. And here is an example of what we would like to try and understand how we can algorithmize. So I have a sheet of rubber over here. I've cut it, but I've not cut it so that all these cuts are continuous. The cuts essentially stop at these vertices, and these vertices I'll describe in a couple of minutes using images, are such that when I pull on this, then the whole object starts to change its shape. And the change in shape you should think of as associated with just rotating the individual squares which are connected to each other. And so if you want to think about it from a physics point of view, this is a very peculiar material where it's made of two phases. One phase is rigid, the other phase is vacuum. The rigid phases can only rotate relative to each other when they're connected at the hinges. The other phase is a vacuum, and that vacuum can essentially have whatever shape you want, and it doesn't cost you anything at all. And so what is the question? The question is, how can you essentially design the folds or in origami, or the cuts in kirigami, which is the goal of what I want to tell you about today, in order for you to go from an initial shape to a final shape? That's a question you can ask. That's the inverse problem. So how do you design the cuts? The forward problem is, once I give you either the folds or I give you the cuts, how can you essentially deploy them in order to essentially solve the forward problem? I'll come back to the forward problem later on in this talk if I have time. I want to start by thinking about the inverse problem, because the inverse problem is what artists have been remarkably good at solving for millennia. Okay? What is it that I'm trying to do mathematically? The sheet, whether it's essentially folded or cut, is flat almost everywhere, except for a set of measure 0, and that set of measure 0 corresponds to the locations where the creases meet or where the cuts meet. And those are along edges and along vertices. So except at edges and vertices, except at folds and places where the folds meet, it's piecewise flat. So the metric is the Euclidean metric. So the only thing that you can do is rotate. Okay, so I can rotate in the plane. I can rotate these facets in the plane if I'm thinking about kirigami. And if I'm thinking about origami, I can essentially rotate these facets about the hinge that's made up. Does that make sense to people?
So the assumption is that where it's not folded, it's
Absolutely flat, and the metric is the Euclidean metric. So Gij is delta Ij. Yeah. I want to introduce that as a hard constraint. I will relax it towards the end of the talk when I start thinking about physics. But from a mathematical point of view, the simplest problem to describe is exactly what you said.
No, but there's a strong, it could be geometrically flat or it could be actually
No.
just affine subspace, right? I mean, is that
I mean it's geometrically flat. So the metric is the metric associated with the flat plane. Gij is delta Ij. It's absolutely flat.
cylinder is
Cylinder is possible, but cylinder is possible in general, but it's impossible when I have basically edges which are connecting one facet to another facet, because that's not going to be allowed, since if I have a cylinder I've curved in one direction, that's impossible when it's connected. A cylinder will be possible if it's free, but it's not possible if I have connections of that cylinder to other pieces. Does that make sense? Ask me later on if it still doesn't make sense. Question?
In the origami case, but that's a negative curvature.
That's correct.
Flat space is going to be zero curvature.
Sorry?
Zero curvature in the flat everywhere.
Exactly.
So
And
where is the negative thing coming from?
The negative curvature is associated with the fact that I've now introduced these folds.
Okay.
And when I've introduced these folds, the orientation and the location and the position of these folds allows you to approximate negative curvature using the folds.
I see.
Okay, and in fact, perhaps I think this is what you're referring to. There's this very beautiful idea, which unfortunately I won't have a chance to get into any detail, which goes back to Riemann and then Nash and Gromov, associated with asking how can I use ideas from convex integration and essentially introduce corrugations of different types at different locations in order to accommodate the effective curvature that I'm trying to approximate, if that makes any
So
sense.
does it mean if I introduce infinite number of folds, will it go to a hyperbolic manifold?
Very good. It could. I'll make that distinction much more clear, I hope, towards the end of the talk if I have a chance to come back to origami. I'm really not going to talk about origami today. I'm going to talk about Kirigami.
I see. So, but it looks like a mapping from a flat space to a hyperbolic thing by introducing infinite number sequence of.
Infinite number, and the Nash-Gromov idea actually tells you you can do that. You can do that, but the way you would do that is to have not only an infinite number but a hierarchy. So you have a self-similar hierarchy.
Okay.
It's non-unique.
Okay.
For every kind of corrugation that you pick, there is a construction that will essentially take you. Mm-hmm. The surface will be smooth in the limit, effectively, therefore, trying to approximate the hyperbolic plane as long as you have an infinite hierarchy of self-similar folds. But as I said, that's really not what I'm going to tell you about today, because it's origami rather than Kirigami.
Okay.
Yeah. Okay. So, what we are allowed to do? We are allowed to essentially rotate, in this case about the edges, about the creases, and in this case about the edges. In Kirigami, I will show you again, we are rotating in 2 dimensions. In origami, I'm rotating in 3 dimensions. I can prescribe the topology of the creases. I can prescribe the topology of the cuts. I'm allowing you to play with the geometry. What do I mean by allowing you to play with the geometry? So if I prescribe the topology, that means the number of, the coordination number of every vertex. I'll choose to be 4. I can choose it to be whatever I want, but in this case I will choose it to be 4 for reasons, again, which I will clarify as soon as we come to the next slide. Once I prescribe that, once I prescribe the topology, I have freedom over the number of cuts, the location of the cuts, and the orientation of the cuts. And those are degrees of freedom that I'm going to play with as a function of space in order to be able to solve the problem of going from shape 1 to shape 2. Okay? And this is, of course, something that artists do very well, and there are some very beautiful things from an experimental mathematics point of view which I want to try and convince you of as being, I think, very interesting. Let me show you an example of a very simple periodic Kirigami tiling of the plane inspired by Islamic art. And in this case, this is a video from a group in Canada. You can see that there is a unit cell, and that unit cell is changing from one to another. Over here you have a set of squares connected to each other by dog bones, and when you pull on it, and you cross some barrier, you're essentially able to switch to a new state. That new state is essentially a deployed version of the old state. You opened up spaces, but otherwise the unit cell looks exactly equivalent. And you go from one location to the other, there is a periodicity. So there were 3 different examples of unit cells, and in each of these unit cells, you were able to essentially rotate the constituents, and by rotating the constituents, you're able to deploy the system, and you're able to get a slightly larger version of the original system. Okay? But that works only if I have an infinite periodic system. What I want to do is to say, now I want to give up periodicity, but I want to have some conditions and some constraints built in, and ask, can I go from any initial shape to any final shape? Like the one that I'm showing you at the top with Kirigami, like this very beautiful object created from a flat sheet of paper, where you essentially cut it, and after you cut it, you fold one place along that hinge right there along the center, and when you fold it, you see this very beautiful building just coming out. Okay? An artist has done this. My question to you, my question to myself is, can I essentially figure out what is the process by which I should cut, where should I cut, how much should I cut, in order for me to be able to essentially find out how to get to a final state like this one. This is on the macro scale, clearly, it's done with a piece of paper. This is an observation of on the bottom of a piece of graphene, 1 atom thick, from Paul McEwen's lab. This is a paper demonstration of the same thing. So they've essentially cut a piece of paper, and by cutting a piece of paper, you suddenly provide emergent properties associated with elasticity. A piece of paper will not stretch at all. As soon as I've cut it, it starts to behave remarkably. It starts to essentially have these effective elastic properties, and by changing the location, the orientation, and the number of cuts, you can control this. The reason I'm showing you this with a piece of paper and the bottom from observation, SEM observations of a graphene sheet, is to emphasize a second point, and the second point is that these systems do not depend on absolute scale. The questions that I'm going to ask you do not depend on the absolute scale. The only thing that matters is that one dimension, the thickness of the paper, is very small compared to the other 2 dimensions. The absolute dimensions are of no consequence at all. As soon as I have one dimension small compared to the other 2, everything I'm going to say from now on is valid. And so there's a power associated with that, which means I can do architecture, but I can also perhaps do graphene Kirigami. And from that point of view, perhaps there are interesting questions associated with physics, like the mechanical behavior, like the electronic behavior of these Kirigami structures, and then from physics or through physics to interesting questions associated with engineering. Okay? So, having spent a substantial period of time on the introduction, let me now tell you about a very simple class of patterns which we want to try and gently deform or strongly deform in order to be able to ask this inverse problem of how to go from shape 1 to shape 2, initially in the plane and eventually out of the plane. So this, for example, is an undeployed compact structure corresponding to having individual triangles which tile some part of the plane. As these triangles rotate relative to each other, shown over here, when I essentially pull on it, these triangles, each one of them rotates, and I find this deployed state, known for a long time. This is a picture from a review. That's with triangles. The same question associated with squares. You start to see, again, a similar kind of picture. Both these are periodic. You can do it with hexagons. You can do it with Islamic tilings of various kinds. And now I want to raise this question of the inverse problem, the first inverse problem, which is how do we control the, how should we essentially, given the connectivity, the topology of the cuts, how can we change the geometry of the cuts, which means the size, the orientation of the cuts, to achieve any deployable state, initially in 2 dimensions and eventually in 3 dimensions. For example, can we provide a new solution to this old puzzle that goes back at least to the Greeks, perhaps to the Indians, I don't know, of how to essentially take a square and circle it. How can I take a square and circle it? And so we know in mathematics there are some very beautiful ways of doing that, for example, which are constructive, associated with the use of the Riemann mapping theorem in complex analysis, but the Riemann mapping theorem is conformal. Here, clearly, you can see that the deformations are not conformal because I'm not preserving angles, and therefore I have to go elsewhere. But perhaps the Riemann mapping theorem allows me to get a good guess at it. Okay? And so what is our goal? Our goal is to modulate the shape of the unit cell, preserving the connectivity because I'm preserving the topology to match the final shape. Okay? How do we pose the problem? We pose the problem by essentially asking how we prescribe the constraints associated with the fact that I want to essentially start with a compact contracted state before I move to this deployed state, whatever its shape is. And that's very easy to see visually. And as I said, it's known to artists. Our only little contribution is to essentially mathematize that idea, or the set of ideas. So first thing is that at every vertex, if it's 4 coordinated, why do I choose 4 coordinated vertices? The reason I choose 4 coordinated vertices is I have a single degree of freedom. As soon as I have 4 coordinated vertices, I have a single degree of freedom, not only at the level of a unit cell, but for the entire tiling of the whole plane. Once I pull on it, all the squares behave exactly the same way, so I have a single degree of freedom. If I had 5 or 6 or 7 or any higher coordination, then I'll have a lot of floppy modes. And I will, if I have a chance, come back to that, but if I don't, please ask me questions. You can also ask questions about how you can have connectivity percolation or rigidity percolation once the number of cuts is itself a dynamical variable. Okay, so at every vertex, the angles must add up to 2 pi because I don't want to open up any gaps. And simultaneously, if I have these edges which are in contact with each other, the 4 edges that I'm indicating with my laser pointer, then the lengths of these edges A and must be equal to B. Similarly, if this is C and D, C must be equal to D, and so on and so forth. And if it's a symmetric configuration, then all of them become basically the same. So the periodic case corresponds to essentially having a 4 square connected object, and the 4 square connected object, essentially when I pull on it, there is one hinge over here, there's another hinge over here, another hinge over there, another hinge over there, the whole thing opens out, which you can see over here. This is the aperiodic situation, but the aperiodic situation still has constraints associated with the fact that this edge is shared by these 2 quadrilaterals, and so must have the same length, and at every vertex, the sum of the angles must still be 2 pi, okay? So we want to start with the periodic case, give it up, and move towards the aperiodic state, but preserve these 2 conditions, and these conditions are nonlinear, and therefore any optimization procedure that I will try and essentially deploy in them will be highly non-trivial, because the optimization problem is going to be non-convex associated with these nonlinear constraints. Okay? Because I want to solve, for example, this Greek question of going from a square to a circle or going from a square to an Easter egg, I also must essentially map and match the boundary. So for example, I'm going from a square to a circle, all these green points must end up at the boundary corresponding to part of a circle over there, the red points over here, the yellow points over there, and the purple points over there. So I have another constraint, and the constraint says that all these points on the perimeter must go to some prescribed location. Okay? I also want to essentially emphasize that the squares, when they rotate, or the triangles, when they rotate, do not overlap, and so I have another condition, and that condition is an inequality associated with non-overlapping, which means that there is some condition on the area. So,
Sorry, could you go back to the previous slide, please? I don't understand where, I don't quite understand where it's toned, the square. So is it like this, or?
Correct.
So then how do I?
If you see this image right here, you will be able to understand what's happening, or for the triangles over there. So, can you see this right there? And can you see this square over here?
So does each square flip over?
Nothing flips over. They all just rotate in the plane. Look, if you look here,
Oh, so they're cut, actually they're joined only at the center. No, where are they joined?
no, they're connected exactly at the points that I'm showing you over here. Okay, so if you're looking at this picture over here, I have a cut here, I have a cut there, and a cut there, and I have a hinge over here and a hinge over there, and so I'm basically trying to rotate every one of them.
Exactly this, right? No.
2 of them are correct, the other 2 are not, because
Oh.
okay, you see what's happening over here. When I rotate this point is that point over there, this point is that point over there, this point now is that point over there, and this point is essentially also that point over there.
Okay.
You see what I'm saying?
Yeah.
Okay? Questions? More questions? Yeah?
Are you allowed to rotate out of plane?
Eventually, but right now I'm not allowing you to rotate out of plane. Yeah, if you rotate in the plane, so those will be hinges, planar hinges. If I rotate out of the plane, then I'm going to have to twist them as well. Yeah. More questions? I want to make sure that this is clear.
It's going very fast.
Okay? You slow me down. All right. So I told you about the boundary matching constraints. I told you about a non-overlapping condition. And now I want to ask you how, or I want to tell you about how we try to solve the problem. We need a guess. It's very important for the first part of this talk to start with a guess. A guess for what potentially might be a way to essentially convert the square to a circle. This guess, perhaps you can essentially see, is a guess which corresponds to a conformal transformation. But the conformal transformation is not going to correctly satisfy the conditions associated with the angles at every vertex adding up to 2 pi, the lengths being conserved. Instead, it essentially preserves angles, and so essentially circles are mapped onto circles, and there is this 1 degree of freedom associated with the scale of the circle, which of course is a function of space. But this guess does not satisfy the constraints, and so with this guess then, what we have to do is to solve an optimization problem. And the optimization problem that we have to solve is associated with taking this guess, using the conditions associated with non-overlapping, boundary matching, and the 2 nonlinear constraints associated with the sum of the angles being 2 pi at every vertex, and the lengths of neighboring edges being the same, use that as an error to iteratively solve an optimization problem until you've essentially got a valid solution. Valid in what sense? Valid in the context of saying that these constraints are mapped and are numerically approximately solved. And once I've got that, then I can of course contract it. And why can I contract it? Because the contractibility conditions have been satisfied, and if I can contract it now, I get this generalized Kirigami pattern. And this pattern now, if I reverse it and deploy it, I can essentially approximate a circle. Is the process clear, what I'm trying to say?
What are the contractibility conditions?
What I showed you before, and I'll show you again. The contractibility conditions are the fact that edges which are in contact when it's contracted have the same length, and at every interior vertex the angles must add up to 2 pi. Okay? I should say that the contractibility conditions have complete analogs in origami. In origami, because at every crease, at every vertex, when I have 4 creases meet, again the angles must add up to 2 pi. And I also have conditions associated with the fact that in origami, because I'm now working in 3 dimensions, I must ensure that every facet which comes together at a vertex must be flat, and therefore its volume effectively must be 0. And finally, there is an additional condition associated with the sum of alternate angles being equal to, turns out to be equal to pi, and I'm happy to talk to you about that. So there is a slightly different mathematical framework in terms of how you write down those conditions, but morally it's exactly the same. I have a bunch of conditions, I want to satisfy those conditions, and I'm trying to solve an optimization problem of going from shape 1 to shape 2. How do I do that and respect the conditions? Does that make sense? Okay. All right. So I told you we need an initial guess. That initial guess, for example, in 2 dimensions can be associated with a conformal map. And I now basically, once I have this conformal map, and I want to emphasize none of these problems have unique solutions. They're all massively non-unique. But once I have a conformal map or any other form of a guess, then I can essentially solve a constrained optimization problem. And the constraint optimization problem has the following constraints: the contractibility conditions associated with the lengths and angles, satisfying some conditions, boundaries matching because I want to go from shape 1 to shape 2, a non-overlapping condition. This is a technicality. This is not important. It's there to essentially get smooth patterns. So in smooth patterns, meaning I don't want my quadrilaterals to be very strongly elongated and therefore have extreme aspect ratios. So I want to essentially minimize a measure of, we call it shear, so a measure of affinity or non-affinity, and extension, how strong or how weakly deformed the quadrilaterals are. This is again something that we can keep, we don't necessarily have to keep. And we just literally take a well-used and at least in some communities well-loved optimization protocol, for example, MATLAB's fmin-con, and essentially just feed this in. So the only contribution so far is to recognize that you can essentially reformulate this problem that artists have basically been using for millennia as a constrained optimization problem. That's the only contribution. Once you do that, then we can use this well-used framework to solve an optimization problem. Of course, as I said, there is no guarantee that I will converge, and in order to be sure that I will converge, I need a good guess, and I will come back and address that question once I show you some initial results. Okay, so here are some results. So here is what I just showed you on the previous slide, a way to convert the square onto a circle, and what I'm showing you when I'm going from from left to right is increasing refinement. So I just basically reduce the size of my mesh, and if I reduce the size of my mesh, I get a better and better approximation to a circle. No surprises over there, and you can see that the boundary matching becomes better and better, so the error becomes smaller and smaller as I increase the number of tiles. That's an observation. A second observation, if you've been looking, and I invite you to now look carefully at these sequence of different iterations, if you look in the interior you see here and here that it's essentially exactly the original simple square domain. But as I approach the boundary, you start to see deformations which become more and more pronounced. Now there's an interesting mathematical question which we have not solved, so this is something which is open, is as the number of squares becomes larger and larger, as the tiling becomes finer and finer, almost all the deformation associated with these contractibility conditions, all the variations from the square pattern are limited to the boundary. So two questions. One is, can you say something about the boundary layer? So from a physics perspective, if you want, what is the size of the boundary layer? And we have some scaling estimates I won't get into, associated with what is the region near the boundary where almost all the interesting things happen. In the interior, it's very boring. In the interior, it's just the usual original square. Question one. And question two is, what is happening at these potentially singular points? Now, these singular points are, of course, a consequence of the fact that I'm taking a square and essentially mapping it to a circle. So there is no avoiding that. But now if I have a polygonal shape, what will happen to these singular points as I map it onto something which is relatively smooth? And we don't have clear theorems. We have some ideas which I would like to essentially, at this point, not talk too much about. Happy to tell you about later. Okay. So, what is the development question?
The number of vertices
be
equal to the number of singular points?
If you use conformal maps, yes. If you use some other kind of guess, no. So this is a question that you have some freedom over, because it's up to you, as I said over here, it's up to you to essentially choose the different types of guesses that you have. There's a massive amount of non-uniqueness. Over here we use conformal maps, and so you will get exactly the same number of singularities because we use a Schwarz-Christoffel way to essentially solve the problem in the initial state.
So in the other cases, the some vertices merge and become one singular point?
We haven't explored that, but I suspect that you can construct guesses where all kinds of strange things like that could happen. I don't want to venture in that direction. Yeah. Okay. So I want to show you something which perhaps ran too fast, and I was hoping it will replay, but it didn't. All right. So look at the deployment trajectory. If you saw the deployment trajectory looked smooth and there was a jump, that is not an accident. That's real. Our optimization framework said that the constraints are satisfied by definition in the initial state and by construction in the final state, because the contractibility conditions are satisfied when it's fully deployed and when it's fully contracted. But I don't say anything about the path. And why don't I say anything about the path? The reason you can't say anything about the path is because of an additional topological obstruction, which I think becomes apparent. Let me see if I can play this again. Okay, so you saw that it was smooth and it jumped. So what is this object that I just referred to that potentially is problematic? The object that I refer to potentially is when I go, for example, in a loop. I go from this square to, or this quadrilateral to that quadrilateral to that quadrilateral to that quadrilateral. So everything around this rhombus vacuum. These are just combinations of rotations. Okay? You can pick any loop that you want, going from any pink quadrilateral all the way around. All you're going to do when you go from one member to another is a planar rotation. The product of these rotations must always be identity. Because if I'm going around a loop, I've come back after however many positions I've essentially crossed. That must be true for all possible states in between the initial and the final. But I can't guarantee that, because I only guaranteed that in the final state and in the initial state. And a consequence of that, therefore, is that in fact, if I put an energy, any form of the energy associated with deforming the quadrilaterals and energy associated with rotating the hinges, that energy will initially go up before it comes down, because I guarantee the contractibility conditions only in the initial state and the final state. I can't say anything about the intermediate states. Okay? And that is associated with this topological obstruction, which is telling you that I have to guarantee, if I really want a smooth trajectory which has no location anywhere along the trajectory where the contractibility conditions are violated, I must ensure that you give me an arbitrary configuration and the product of rotations for all loops must be identity. And I have not told you how to essentially do that so far. Is that clear? Okay? And in fact, in general, you can't do that. Yeah? Yes?
Are there many other paths, and in all paths?
What do you mean by many other parts?
Many other, between the initial and final. This video shows one way of going. So I'm saying, are there multiple paths to go from
No.
initial?
Very good. Yeah, no, because as I told you, by construction, this system has effectively a single degree of freedom. So when I essentially pull on the system, all the squares rotate simultaneously, and when they all rotate simultaneously, you have a path which takes you from the initial state to the final state.
In this system, in other systems, there could be multiple paths.
No, if I have four coordinated cuts, four coordinated vertices, you will always have a single degree of freedom. And you can just do a counting argument, okay, because you have four facets connected by a set of edges. You just count the number of degrees of freedom in the plane. You have 3 degrees of freedom for each one. You account for the constraints, you have single one. If I have more than 4 cuts, then I will have multiple paths. Okay, because I can have floppy modes associated with the fact that I can rotate some of the interior squares without affecting anything else. But in this case, because every vertex has exactly 4 cuts coming together, once I basically rotate at one location, I rotate everywhere.
And in such problems where there is an ensemble of paths going from one to the other, is there an interest in understanding which is the most optimal path?
Yes, yes. Please ask me that question at the end. Yes,
Thank you.
yes. Yes, there are a lot of questions from a statistical mechanical perspective associated with how many different configurations there are in the intermediate states, and is there a natural optimal way of rigidifying the system so that I effectively have, for example, 1 degree of freedom. But please ask me that question if I don't answer it at the end. Yeah. Okay, so this is numerical. Can you essentially build it? Okay, so Gary Choi, who's a graduate student working with me, essentially took this numerical algorithm. We sent it off to somebody who can essentially cut a sheet of rubber with a laser, and they gave this back to us, and what you see is what Gary's hands are showing you. But you can see, or maybe you can't see it, but I'm going to tell you that in this case, I pull on it, it expands, and if I relax it, it comes right back. And the reason it comes right back is because this is not a problem only in geometry. Now this becomes a problem in physics as well, because when I essentially pull on it at the locations where the squares meet, I am deforming them. Okay, and if I'm deforming them, that means I'm putting elastic energy into the system. If I'm putting elastic energy into the system, the elastic energy is essentially going to go up, and if I relax it, it wants to come back to its ground state, and the ground state is the contracted state. So that means that now, by controlling the elasticity of the hinges, I can control whether or not I'm monostable or bistable. Question?
I think so the bistable means the end is also
2 states are both stable.
the both ends.
Yes, but in between the energy goes up.
So in
And
this case, the end is also stable? Or?
no, only one end is stable, and so this is monostable. If I pull on it, it opens up, and I relax it, it'll fall right back. And so now there is a question, and the question that you can ask is exactly the question that I think you're alluding to, is how do I essentially dial the physics associated with the elasticity of the hinges so that I can go from monostable to bistable to an infinite number in between. And the infinite number is not possible because of the constraint that I told you, because I have to guarantee that all loops are essentially, products are going to give rise to identity, okay? And so clearly this system is technically not what we can call rigid deployable. Rigid deployable means that I have a one parameter family. In this case, I have an initial state, a final state, and that's it. And I'll address how can we start thinking about this. Okay, so here is now a little graph showing you what I was talking about just with words. In this case, this is a measure of the energy associated with the angle that I am imposing at the vertices which are connecting the squares. This is the initial state corresponding to the contracted case. This is the final state. By definition, up to whatever tolerance you give me, I can guarantee that the contractibility conditions are satisfied, and therefore the energy also goes to 0 or as small as you want it to be, and the energy increases before it decreases. So this is bistable. Okay? And it's bistable because, as I said, in between, this topological obstruction condition is not satisfied, so there is an obstruction, or equivalently, I have to pay a price. As I change a single parameter, which is the stiffness of the hinge compared to the stiffness of the edge, you can essentially go from bistable, corresponding to, for example, I can't see the color, blue. As I make the hinge stiffness more and more, I essentially switch from something which is bistable to something which is monostable, which is exactly what I was showing you previously. Okay? You can ask the question, okay, I did this now with squares. Can I do this with other unit cells? And here are some demonstrations. The answer is yes. You can do this with other unit cells. You can also go to different shapes, like an Easter egg. And then you ask, in mathematics and in physics, we know that if I wanted to tile the infinite plane, I have the wallpaper group. I have 17 members of the wallpaper group, and the 17 members of the wallpaper group allow me to tile the infinite plane. Now I can ask, for each member of the wallpaper group, can I essentially construct a Kirigami deployment? Okay? That's just a labeling. I don't want you to pay attention to it. And here we have a little theorem, and the theorem is that for every member of the wallpaper group, there exists a deployable Kirigami pattern. So I can essentially deploy it, and here are all 17 members of them, and I've shown you simply the unit cell. And again, if I give you the unit cell now, and I pick any member of this, and now you tell me I want to go from shape 1 to shape 2, I pick this unit cell, I write down the contractibility conditions associated with that, and I then just crank through the optimization algorithm again, and I can give you now a way to go from shape 1 to shape 2, choosing any one of these. Okay? I don't want to spend too much time, but I hope that you can clearly see it's very, very easy to generate these question.
So the one for P3 seems to have a hole in the initial state, holes in the initial state. Is that
which one?
P3. So the initial state seems to have.
I think that was for visualization. Good question. And can I come back to that at the end? Yeah, I don't remember exactly why it's being shown this way. You're absolutely right, it shouldn't. And I don't know why this is showing what it is.
So just the hexagon there would just rotate. In each hole, if there was a hexagon, it would just probably rotate.
Yeah.
I mean, it looks like maybe.
Let me not try to answer the question now because I don't remember. I will come back to this later on. Other questions? Okay. You can also ask about, of course, if I have periodic structures that tile the plane, can I have aperiodic structures? And I'm sure everybody over here knows about the Einstein. I don't have anything to say about the Einstein, but we can also ask, can you construct quasi-crystal Kirigami? And here is a representation of one possible deployment of the classical Penrose tiling associated with a 2-family member which will tile the entire plane aperiodically. As I said, with the Einstein, we asked the question, this recent development in a monotile, which can essentially tile the entire plane. Don't have anything to say about it. Okay. People ask me about 3D Kirigami. So can you do this in 3 dimensions? Of course, if I'm doing it in 3 dimensions, now I have to force the hinges to essentially start moving out of the plane. But I still make all the other conditions exact. That is to say, contractibility of angles, contractibility of lengths is still exactly what I want. So what did you expect? You would expect that when I try to deploy this in the 3rd dimension, where is all the curvature going to go? And the answer is all the curvature goes into the vacuum, into the holes. Because I have to maintain all the facets and keep them flat. So again, from the physics point of view, I like to think of this as a very peculiar material where one phase is rigid and the other phase is a vacuum. And the only thing that you can do is move the rigid phases, and the rigid phases, the only possibility is to move them by rotations, and in this case I not only have planar rotations, I have 3-dimensional rotations, okay? And again, the algorithm that I told you allows you to essentially move into the 3rd dimension, and here are some examples of how you can approximate surfaces of negative, of positive, and of mixed Gauss curvature. These are what on the right side I'm showing you is where is the Gauss curvature, where is the mean curvature hiding, and it always sits as it must in the holes because the rest of it is flat. And then you can essentially build these things physically as well. And here is a very nice example of something which, for example, you might want to wear around your neck as a necklace. Okay. So far, I have shown you one contracted state and one deployed state. Now I can ask, can I be greedy? Can I essentially have one contracted state, one deployed state, and then when I contract it, you go to a new contracted state? Can I have 2 contracted states? And I want to emphasize that the 2 contracted states shouldn't be just symmetry related. They should be fundamentally different ones. So can I do that? And in the case of the square pattern, which I think you tried to essentially illustrate, when you open it up, you keep opening it up until the squares become 45 degrees with each other, but you can keep closing it, you can keep pulling on it, and the whole thing will close on itself. In this case, there is no distinction between the 2 contracted states because they're symmetry related. But in general, they don't have to be. So can I now use Kirigami to design multiple contracted states where I go from one to the other? In this case, the multiplicity is exactly 2, and it is exactly 2 because each edge, each vertex is 4 coordinated. If I have higher coordination numbers, now I may be able to move to go from one contracted state to maybe 2, maybe 3, and so on and so forth. So can we have distinguished contracted states, and can we have reconfigurable Kirigami? I want to emphasize that everything I want to tell you about is sort of inspired just by asking these questions. There are all kinds of interesting implications from the point of view of architecture, from the point of view of antenna design, and whatnot. I don't really have anything to say about this. Okay, so here is what I was showing you, what I was telling you about with squares. So initially, these 4 angles are in contact with each other. I open it up. When I open it up, these angles start to move apart. It's fully open, fully deployed. I continue to close it, and these angles, which were originally far away, have now come to the interior because I just rotated all of them. Okay? And these edges, the outside edges which are not in contact with each other, now in contact with each other. So all I have to do is to just augment my constraints and say, if I want a second contracted state, not only are the interior angles going to add up, but the exterior angles are going to add up. Not only are the interior edges going to have the same length, but the exterior lengths also have to be the same. That's it. So I just add a set of additional constraints associated with angles, these gammas, and associated with the edges which were not originally in contact, which will come into contact. And again, I say I don't demand periodicity. All I demand is that this be applicable locally everywhere I go, but I don't demand that each one is a copy of the other one up to a translation. Okay? Same procedure again, and I want to show you again examples. So you keep opening, you close it, and it closes to something completely different. Okay? And again, you can see the jump. Okay? Again, it opens, and then it suddenly closes, and again, it's because the topological obstruction comes in the way. Okay? And here I'm showing you the energy. And so the energy is very interesting. Previously, we had one state, a second state, and the energy went up and then came down. Now, the energy goes up, it comes down. You have, this is not zero energy. It has got a finite energy, but it's very, very small. So it goes up, it opens, then you have a whole sequence of states which are almost energetically equivalent and very small, but they're not quite. And then just before it closes, you see a jump. Let me show you again with the simulation. So it jumps there, and then jumps at the end. Okay? And here's what you have. Now this object, I'm going to call a chimera. It's neither one nor the other. It's neither what in classical 19th century mathematics and in engineering would be called a structure, so a system which actually has no zero modes. So it's neither a structure nor a mechanism. A mechanism would be a set of links which essentially have zero energy modes associated with them. So in this region, it's behaving like a structure. Here, it's behaving like a mechanism. Here, it's behaving like a structure. So it's neither one nor the other. Question?
That means in between the large number of states
Are equivalent.
having the same energy.
Precisely. And so all that's happening is that you're just rotating the facets relative to each other. You're not deforming them at all. Exactly right.
In physics, people call it as a massless mode is there.
That's exactly right. It's a Nambu-Goldstone mode if you want. It is equivalent to a mechanism. Yeah, all these are equivalent analogy. Yes, exactly correct. Yeah. So it's almost massless over here, and it has high mass at these ends. So it's very beautiful. It just comes out completely naturally, and in fact, you should expect it. Okay? All right, so now I can ask, this is not rigidly deployable again. Okay, because I had to pay an energy. So I say now I'm going to be even more greedy. I want to say, can I essentially make this rigidly deployable? So I make it massless all the way. So I now have a one parameter infinity of modes which essentially connect the two states. And the answer is, again, told to me by geometry. And the way we think about this is to recognize that these are all boring. Okay, all the squares are boring because they're rigid. What we're really doing is playing with the vacuum. We are playing with the gap. And we are playing with the gap by basically just asking what is happening to these 4-bar linkages which are essentially connecting the squares to each other. What happens when I go from one location to the other? And if I want rigid deployability for all intermediate configurations, I must have the lengths be preserved and the angles be preserved, like I told you at the beginning. Okay? So I have a theorem. When is there a rigidly deployable path? And there is a rigidly deployable path when I have a situation like what I have shown you in the center. I'm showing you this pictorially, but you can essentially take all these ideas and convert them to something that you can essentially prove. And the pictorial idea, I hope, is very clear, because in this case, as I open the system, it opens up symmetrically, and then it closes symmetrically. If I have a situation like this, what's going to happen when I open it is that I'm going to have to pop it open, and I'm going to shut it closed, just because of the non-convexity, just because of the fact that I have this kink in one direction or the other. And that condition associated with this intermediate set of configurations, you can write in terms of a whole set of algebraic constraints associated with the angles. It's not worth getting into, but I hope you get the intuition by looking at this picture in the center. So here is a theorem which says that a reconfigurable Kirigami pattern, so one which has two contracted states, is globally rigid deployable, globally in the sense I have an infinite number of intermediate modes, all of which are equivalent and all of which are massless. Okay, is only possible if I satisfy this condition, set of conditions, or equivalently, I really have to think about linkages. I don't now anymore think about the rigid phases, I only think about the vacuum phase. Okay, and the loop condition is just essentially what I was telling you about, that the composition of rotations of all internal 4-bar linkages must combine to identity, and I guarantee that. I force that as a constraint. I can build that in. This one more condition, okay, in my optimization algorithm. So let me show you now an example. Okay, let me show that to you again. Two distinct states. Let me show you a physical realization of that. Let me show you the energy. Okay, the energy is now flat and zero all the way through with a single degree of freedom. Okay. These are all linkages. Yeah. And now I'm going to show you the solution to the Greek problem, a new solution to the Greek problem of essentially taking a circle and converting to a square. And now the square and the circle are both closed, compact. It's not that previously it was deployed, it was open, but in this case, I opened the square, and then I closed it, and it became a circle. And I can become more and more accurate as I reduce the size of the facets, so I get higher and higher degrees of approximation and accuracy. Correct. Correct.
Towards the end, you compressed it at the top.
Oh, that was probably because in reality, we cannot make everything perfect, and if you don't get everything perfect, sometimes there's a tendency for things to jam a little bit, and you push it through. That's just because reality is different from mathematics. In a good way. Very good way. It keeps you honest. Okay, let me play this last movie again, which I like very much because it shows you how to convert a square to a circle. And I just like it because every time you see it, it sort of blows your, at least it blows my mind, even though I've seen it for a few years, that you keep rotating it and you go from the square to a circle. Okay? And, okay, good. So I have about 5 minutes left. And now I want to completely switch tacks and tell you about what I said at the beginning was a very difficult problem to solve. And the difficult problem to solve was to have a good initial guess, either in the two-dimensional problem or in the three-dimensional problem. And if I don't have a good guess, I have no guarantee that I'll essentially converge. I can't solve the optimization problem and essentially guarantee that to whatever level of accuracy I want, I satisfy these constraints, contractibility constraints. So how can you do better? And the answer is to turn in your head what we do in mathematics and physics all the time, is to think instead of solving an optimization problem, I solve an evolutionary problem. So I switch my mode of thinking, and sort of mathematically it's fundamentally different. So instead of solving an elliptic boundary value problem, I solve a hyperbolic problem. In the hyperbolic problem, I essentially have a propagating front. And the inspiration for this came because I spend, in fact, most of my time nowadays thinking about biology, not about these problems. And in biology, everything happens through growth. Nothing happens through optimization, almost. Okay, I start out as a single cell. You also start out as a single cell. In 9 months, you developed into a complicated embryo, and that happened through growth. So there's an evolutionary process. I don't mean evolution in the sense of biology. I mean evolution in the sense of mathematics, where you're essentially adding matter, and you're adding matter in complicated ways. And by adding matter in complicated ways, you end up with these remarkable structures morphologically. So instead of solving this global optimization problem, where I want to try and understand how to satisfy the constraints everywhere, what if I turned my head 90 degrees and said, I start with a single unit cell, let me say a quadrilateral. And then I add to the quadrilateral a set of quadrilaterals on the boundary, which guarantee that every time I add them, I satisfy the contractibility conditions, but I only satisfy them in that corona. Then I add the next set. And then I add the next set, and so on. Okay? Can I now solve the same problem that I wanted to solve, but now from the point of view of a marching algorithm? I essentially solve the problem by thinking about it as a discrete wavefront, which is moving out from the square, and at every level, I essentially guarantee and satisfy the conditions. And the short answer is yes, and not only that, I am able to get around this complicated nonlinear optimization problem. It turns out you can just replace the solution by just a series of matrix operations, and the matrix operations are just essentially products of matrices, which I have to make sure I use to guarantee the contractibility conditions. So I'll only show you a visual picture of this. I hope I've convinced you that the key in solving the problem is to recognize that you're working with the empty spaces. You don't have to worry about everything else because everything else is rigid. You don't have any freedom over there. All the freedom is associated with working with the empty spaces. In the context of thinking about it from the point of view of linkages, I just have to worry about this as a 4-bar linkage. And so imagine that this was my initial unit cell. I have some freedom to choose the shape of these rigid objects if I'm trying to march in one direction, if I'm trying to march in the other direction. And I have to guarantee that these empty spaces must close. Okay, so when I squeeze them, they are contracted. Which means that if I give you 2 of these, for example, the one shown in black, the other 2 shown in dashed lines are immediately frozen. I have no more freedom associated with that. And I can do that in one direction, I can do that in the other direction. And what degrees of freedom do I have? Because I'm working with size and I'm working with rotations, it turns out that you have a sequence of concatenated 4-bar linkages where you have 2 parameters, one parameter which corresponds to how much I'm rotating when I'm going from this x0, x3 and x0, x1 to x3, x2 and x1, x2. How do I go from x0, x3 to x1, x2? I have a rotation and I have a scale associated with how much I'm essentially changing the size of the object. And so I can then move along in one direction, I can move along the other direction, and you give me any complicated shape in this direction, you give me any complicated shape in that direction, I can just march along and satisfy that. Once I've done that, I can go to the next level and do exactly the same thing, then I can go to the next level and do exactly the same thing, and now I have a marching algorithm. And so as I said, it's a fundamental change in perspective, mathematically switching from an elliptic to a hyperbolic problem in a discrete setting, if you want, where one now is thinking about one direction as time-like. I can then design things. So here is a crazy shape mapped into another crazy shape, and the crazy shape is mapped through this deployed structure. And now, by working with the aspect ratio, so as I said, there is an aspect ratio associated with scale, and there is a rotation on top of that, I can convert a heart into what, at least to my mind, looks like folded hands or Batman. And by playing with the amount of eccentricity of the objects themselves, you can get some very, very strange shapes. So this is just a demonstration. And again, you can solve the problem of going from a square to a circle. And now notice that I've given up all these conditions on conformality and so on. I just pick an arbitrary initial guess. And once I have an initial guess, I can just essentially corona by corona go around it. So in this case, I started with the initial square and then added a whole bunch of, in this case, 2 layers. And by adding these 2 layers, I get an approximation which essentially is able to tile the circle, and I can go smoothly from here to there. And if I add this rigid foldability constraint, not only goes smoothly, everything in between also is a zero energy mode. Okay, so I think I have run out of my time. I will simply tell you that everything that I've told you so far was associated with prescribing the topology of the edges and playing with the geometry. You could turn the whole problem around and say I prescribe the geometry and then control the topology. Control the topology is who's connected to whom. I think there was a mistake made in the context of the original demonstration. That was a mistake in topology. They made a mistake in terms of who's connected to whom. And I can ask now, by changing the question, by playing with who's connected to whom, is the system fully connected? You know that if I take a piece of paper and I cut it, and the cut goes from one end to the other, I break it into 2, but if I don't, it will not be fully connected. I can think about a connectivity transition, percolation transition. I can think about a rigidity percolation transition. Rigidity percolation will be at the end, I have 1 degree of freedom. Somebody asked me a question previously if there are many degrees of freedom. The answer is, I can now ask this from the point of view of percolation theory, but I have run out of time. I'll simply tell you that we can solve that problem in a deterministic setting by asking what is the smallest number of links that I need in order to rigidify the system so that I have a single degree of freedom. We can prove some simple theorems on that, and we have questions associated with how rigidity or connectivity percolate through the system when I essentially start with a set of squares and I gradually add bonds to them. Okay, so now interesting connections to statistical physics, but I won't tell you about them. And I won't tell you about this either because I've said, okay, so this is all so far just geometry. You can ask questions about the mechanics. I'll show you some images. So you have a single sheet, and when you take a single sheet, you can essentially create a kabuki mask with it. You can ask properties about the kabuki mask, but I will not tell you about this. I will just close with this very nice result, which I think is also intuitive, and we were helped in the proof of a theorem by Chen Han and Marta Lewiczka. And here is the theorem, and here is the observation. The observation is the following. If I take a sheet and I make random cuts in it, now I pull on the sheet in an arbitrary direction, what is the response? So small deformations, the response is not particularly interesting. For large deformations, something very interesting happens because force chains essentially have to percolate from one end to the other, since I'm pulling at these 2 ends. The forces can't percolate through the cut, so therefore you would expect that the forces would percolate all the way to the edge of the cut. And if they percolate all the way to the edge of the cut and I pull on it, what's going to happen? The sheet is going to deform out of the plane, and these polygonal shapes corresponding to how the forces are propagating become straighter and straighter. So you essentially have the possibility of geodesics, which are piecewise linear polygonal objects in 2 dimensions, become straight in 3 dimensions. And this then you can use, if you care about such things, to essentially hold on to pieces of the world, tennis balls and whatnot. And we've been exploring ideas from soft robotics and also soft architectures, where if I pull on it, it opens, and so it becomes a window. Okay, let me stop. I told you, I hope, a little bit about this remarkable, very beautiful art form, Kirigami, which as you start unpacking it, makes all kinds of connections to any part of mathematics that you care to. Optimization theory, ideas of rigidity control, topological control, shape control. I didn't really have a chance to tell you about the continuum mechanics, but there are interesting questions. There are questions associated with statistical mechanics as well. There are lots of questions still. You can ask, is there a continuum theory of this framework? We don't know at this point. I told you about additive origami. I told you that you can prove theorems about the fact that you can essentially approximate any shape in 2 dimensions and any shape in 3 dimensions using the additive approach rather than the optimization approach. And then there are 3-dimensional analogs. There are prismatic solids. If I take a bunch of solids and I connect them, if I open it, pull on it, how will it open? Can I also link it with origami in addition to Kirigami? Don't know. So let me stop here and tell you that everything that I have had the pleasure of describing to you was really the work of some remarkable graduate students. Gary Shaw.
Positive definite matrices?
Yes.
Okay.
Yes. It will be positive definite matrices, but definitely not unitary. Yeah.
So initially when you, so to map to circling the square, so as you increase the more and more cuts, so we see that inside also there is the same figure. So is this that if we have, let's say, sufficiently large paper or something and we have large number of cuts, so can this thing only done by cutting on the boundary?
Yeah. Yes. So that's a more complicated version of the problem, because now you're telling me that I only put cuts at some particular locations and don't put cuts at another location. Sure. You give me an initial guess and I can work with that guess to essentially tell you how to optimize the number, the location, and the orientation of the cuts.
So one more thing.
So there's a lot of non-uniqueness in this problem. I want to really emphasize that. You have so many different ways of essentially starting, and for each way of starting, the optimization problem will essentially, our optimization solution will take you in one direction. Similarly, if I'm thinking about the additive framework also has a massive...
It's a contracted state. So is it the initial boundary condition plays?
I understood your question. Can you try again?
Let's say I have an initial square paper. So can I make some cuts so that it will have some another, so that it will have different
potential path which takes you from the initial arbitrary state to a final arbitrary state.
So I am asking, let's say I want to have to a different contracted state.
Beyond 2, unless I change the topology of the cuts. If I change the topology of the cuts, now I have the possibility of going from 1 to a second, potentially to a third, but then I can't guarantee that all no.
So there were some shapes where the final shape went back to the initial shape.
Energy associated with the hinges.
Yeah, so, but then there are some transition where the energy is constant, but there is also the energy should be there, no? Like.
No, the energy is 0. It's not just constant, it's 0, because I have no energy associated with the rotation of the hinges. I must guarantee that the product of rotations is identity, and if I use that additional constraint, then I have a 1-parameter infinity of solutions, all of which are energetic.
Twisting the...
In a physical setting, what that means is that you have to have hinges which are very, very soft. So the way to essentially have soft hinges is you don't glue them, you essentially... On the right side, you essentially use... actually, I don't have... No, this is wrong. So I don't have an image of that. You move it into the 3rd dimension. I think there was a question there as well.
I was just curious that instead of
cuts which are curves, then the simple answer to your question is just replace the cuts by curves, cuts by straight approximations. Okay, and if I replace them by straight approximations, then I can just in the previous case when I had straight cuts, the straight cuts always met at vertices. If I have a curved cut, now some of the cuts don't meet at 4 coordinated vertices, some of the cuts only meet at 2 coordinated vertices. So we have really not thought that through. Contracted state to one deployed state, and the answer is almost certainly yes.
So the shapes.
The end shapes have nothing to do with degrees of freedom.
So you keep tuning.
Have 4, you repeat that again and again through the entire domain, L by L squared.
You have this.
Forward or backward?
You have 2 different end shapes, but in between you had many, I think the 2D.
This one?
This one.
Okay.
So you have those, I'm assuming they are colored by some, what is the coloring in the center for
the coloring is energy, so blue is low energy, so essentially almost 0, and red is high energy, corresponding to these peaks over here.
So what I wanted to know is that if
here, there are many equivalent states.
So if I sit on one of the states,
where?
Is there any one of the 3 shapes?
Yeah.
Is there a way for me to know a priori what transformation I should do that I go to a equivalent energy or the end point? Is there a way for me to know?
I don't know what you mean by what transformation. I've frozen the topology over here, so there is no transformation that's possible. The only thing I can do is deform.
In the deformation, how should I deform, whether I should go to 0 energy state or the next transition? How would I know when I'm sitting in one of the states in between?
This object has a single degree of freedom. It's not a projection. It's literally 1 degree of freedom. So I don't still understand your question.
But they look very different. So I'm trying.
They do look very different. Yeah.
Yes.
And they look very different because I'm essentially pulling on the system, but it's not like I have rattling degrees of freedom in the interior. All the facets are essentially deforming, some more and some less, but they're all rotating.
Okay, so maybe if I'm looking at the lifetime
of Kirigami to understand its folding or something.
Maybe. Deliberately avoided any discussion of energetics for the most part. A one-dimensional backbone onto which you have amino acid residues and which are connecting. So in spirit, it is similar to this. In practice, it's very different because the constraints appear differently. But yeah, I'll leave it at that. Does that begin to address your question? Yeah. But that's a very different perspective compared to what protein folding people do, which is heavily engineer the energetic interactions, and that's something that this approach completely avoids, for better and for worse.
Yeah. So, one can naively think of in kind of generalizations, mathematical abstract generalizations, like going to a higher dimension in one way or another way. So, one way I'm imagining is like you are starting with a flat paper. What if you start with a hollow sphere, cut its surface in some way, or
Yes.
If you start with some such non-trivial surfaces, what can you do with that? Can you map all problems in flat to problems in
the answer is yes, and here's how. So those contractibility conditions, I can replace by conditions on a discrete version of Gauss-Bonnet. Okay, so if if I have contractibility conditions which tell me, oh, I am contracting, but when I'm contracting, I contract not onto a flat sheet, but I contract onto locally something which looks conical, and locally something which looks conical or part of a sphere. So I now have a discrete version of the Gauss-Bonnet theorem which tells me as I go around these loops, what happens when I essentially rotate from one facet to the other. So all I have to do is to replace the contractibility conditions with their appropriate generalizations to curved, discretized surfaces, and everything will carry through. I say everything will carry through. We haven't really done that. We've just started thinking about that problem. So that's one possibility. In the context of the connectivity problem, one thing that we have been thinking about is imagine that I have a set of pebbles, but these pebbles are polyhedral. And now I bring the pebbles, polyhedral pebbles together, and I glue them. There are many different ways of gluing them now in 3 dimensions. Unlike in 2 dimensions, it's very, very just simple way. I just glue them at hinges. In 3 dimensions, the vertices are multiply connected to many, many edges, so I can choose to connect some and not others. How many different configurations are there associated with opening and closing? So, don't know. Again, we can use these ideas, but we have to now very carefully rethink the constraints. So the main obstacle, in fact the only obstacle in the whole process, is to understand that you have to just rethink what are the contractibility conditions, and once you have the contractibility conditions, can you figure out interesting ways of solving this inverse problem with guesses. If I think in terms of additive approaches, I just don't know, because additive approaches are something we just started thinking about a couple of years ago.
Thank you.
Okay, so let's thank Maha for this very fascinating talk. Thank you.